pharmacological principles. So I think I'm not sure if we should be able to, for sure we're going to be able to finish between the two classes, but we'll see how we're going to go today. So we went through part of the pharmacokinetics and pharmacodynamics in the previous class, and I think only by that absorption, excretion, metabolization, it'll give you a lot of insight in terms of how you actually will determine what type of drug you use. We're going to see right now like some of the examples of the antibiotics, and you end up looking and you can see, for example, from the antibiotics that although we're going to go into how they act, what types they are, and so on, by the end, which one you're going to use is going to be a lot because of the kinetics and dynamics. Okay? And how toxic they are, if they are for a certain organ. So, and even if we have certain kind of classes of, not only in terms of, how molecularly they look like and where they act as we divide antibiotics, we're also going to have like some differentiation of those antibiotics based on how they actually are excreted and how they're removed from the body. So I mentioned this, in the previous email because it tells you in some ways, pretty good. You're going to have a pretty good idea of how most of the antibiotics go. Some they really but they mess a little bit with metabolism of the bacteria. Some of them will be cell wall. Some of them will be DNA and RNA synthesis, or in general synthesis. Mass with the DNA or RNA synthesis of the bacteria, especially DNA. And you're going to have a few that are like protein synthesis. What is like the idea here is that if you really think about all of that, and that's why it's not so intuitive to know, many of them and all of these, you can probably say and go and say, you know what? A lot of them, they can actually kill bacteria. Okay? But many of them, what they are going to actually do is to stop the growth of bacteria. And you may think this is, the same way that you have all these differences in how they are metabolized and how they are, excreted. If you really think about the use of a certain antibiotic, if they are bacteriostatic, which basically means they stop the growth of bacteria, or if they are bactericidal, that means they kill bacteria, it may be important, not all situations, but they may be important in some situations where you would like to take a certain care of how this bacteria may end up leaving your system. Okay? So all of those, and you're going to see that for the next 10 slides or so, you're going to see lots of names that you are somewhat familiar, based on the types of antibiotics that even yourself has taken or you have given to your dog or to animals that you may have. So let's start with one, sulfa. And sulfa is probably one of the earliest known antibiotics, and some of them that were at least very widely used. Do you remember, for example, if you have seen like movies of war, you always have like in the front of the doctor, and they used to carry like powder, like a bag with a powder in it. I saw this in many movies. The guy gets shot, and the doctor goes there and starts pouring that into the wound. And it's not like, some of them has a little bit of vitamin K because of coagulation, but a lot of that is sulfa. It's because you use that as to avoid but the guy just got shot. I don't know exactly what that will do. Maybe I should look into that, but I don't see that makes any sense. But at least the guy is doing something. But the thing is, it acts on folic acid system. You're going to see that sulfa always, very often is used with another kind of, antibiotic or chemical, and they both work in some ways in the synthesis of folic acid. So they tend to be what we call bacteriostatic. So they stop the growth of bacteria. They don't necessarily kill the bacteria. Okay? They are what we call broad spectrum. And this is the kind of stuff that we have in many of them, like when we talk about the types of antibiotics, is like this. They are, where do they act? Sometimes how they act. If they are broad spectrum or if they are narrow, in terms of they only act on positive or negative. They are bacteriostatic, and then eventually we say where they may act, and so on. So in this case here, it acts almost everywhere. It has broad spectrum. You're going to see that many of the antibiotics we talk about, they tend to be more broad spectrum. And now, do I need you to know these things here? Of course not. Okay, you don't need to know these agents. But this is the way, and this is the kind of stuff that is kind of, it is sort of very typical from our way of doing medicine. We tend to correlate a certain type of antibiotic to a certain bacteria in a certain organ. Okay, that's how we choose what type of antibiotic it goes. Why? So when it comes, like for example, sulfonamides can be used, soft tissue, intestinal infections, urinary tract, respiratory infections. The thing is, the way you can take that drug and what organs it can treat, it tells you a lot about the absorption and actually the uptake of that molecule through all tissues. Because think about this. If you're giving something that is oral, the molecule has to have a certain molecular, it has to be a certain molecular type that is easily absorbed. So, for example, for you to have things that are easily absorbed, it cannot be strong cations or strong anions, because if there is one of the two, you tend to have problems absorbing into the cell. Okay? So they tend to be more like weak acids or weak bases or even neutral molecules. Then they can be more readily absorbed. Yes, they have to be less sensitive to pH in some cases. So some of those drugs, if it is absorbed orally, it means that it has to, at least in part, resist pH 3 or 2, even of your stomach, for example. Okay. Now, the other part is like, if it is respiratory infections, if it's urinary tract, if it's soft tissue, intestinal infections. So all of this means one thing. So for example, let's say you have a respiratory infection. In order for you to reach, if it goes from urinary tract to your gut, to your pulmonary system, it means that it really has to spread well in your body, which basically means it has to basically pass lots of barriers and it has to relatively easily cross membranes around your body. Urinary tract, this is one, and we're going to take a little bit more time in this one here. The next ones will be, as we repeat, will become easier and easier. But urinary tract infections is also the other thing that is, it's kind of a, because your kidneys are the major source of excretion, the major site of excretion for most of the drugs, and actually for most of the antibiotics. You're going to see 90% of them, the major route is going to be urine, and then you're going to have a few of those that have like feces or the biliary system is a major source of excretion. But the urinary tract, so have you ever heard about, for example, you taking cranberry juice to treat a urinary infection? Okay? And what is the deal with cranberry juice? Why is it effective in the, for example, especially urinary bladder infection and so on? What is the take from that? I don't know. We never discussed this, but what do you think has to be special about cranberry juice? Go ahead. Go again.
If we were easily absorbed through the glomerulus.
So basically, we're saying is that it has to be enter the glomerular filtrate, has to enter the Bowman's capsule, but it has to stay in it. Does that make sense? Or do you mean it has to be reabsorbed?
No, like it has to stay in.
It has to stay in. So that's precisely one of the things. It has to be a molecule that somehow it doesn't get reabsorbed, all that quickly. Okay. The other one is that, cranberry, the molecule, and those are some of those phenolic acids and so on. They have to actually go through your body without being so much metabolized. Because this is the other thing. For example, in order for you to have, let's say, an antibiotic that reaches, for example, your urinary bladder intact, it means that, once you took the pill, that thing went through your liver, it went through other places, but eventually ended up in your urinary bladder. Either is the metabolite is the one that is making the action, or is non-metabolized. So just the fact that you have something that works here, it means that, you have a few things that gives you a certain lead into how that thing is absorbed, how that thing is metabolized. Again, it's not clear cut. You're going to have cases where, this thing is supposed to be bacteriostatic, but it's bactericidal. That's okay. You're not supposed to know every detail for every drug. And eventually, what happens is that as you get used to these names and the treatment of certain conditions, it's not like doctors know everything about all these antibiotics all the time. They're used to it. You have a respiratory infection, so you're going to take it. You have this thing, you're going to take that. You have this thing, you're going to take that. Theoretically, the best way would be what? At least to see if the type of bacteria that you're treating is resistant. Do a laboratory test and say, hey, this thing is not. But that is time consuming, it's expensive and stuff. So in general, we treat stuff with a bazooka. So we kill whatever that is, which causes another set of problems, which is resistance for the most part. So this is, now going back to how it acts, broad spectrum, acts on folic acid synthesis. There's a certain strain or group of bacteria that tends to respond better, either because they are bacteria that has not much resistance to it, or they tend to cause infections in sites that make more sense for sulfa to be used. Okay, so there's the two things. You have one thing, this molecule here that you call trimethoprim. And if you look at, if you have ever taken sulfa, probably at some point you have taken, normally it's always sulfa, ponamide, or sulfa plus trimethoprim. And this trimethoprim is basically a molecule that does the same. It acts in a slightly different route of folic acid synthesis. And when they're two combined, they act in a synergistic way, because they act more or less in the same pathway of a certain molecule, folic acid, but in different streams of their cascade of synthesis. So lots of these things, Pastorella, Proteus, Histophilus, some of these Haemophilus. So all of these, for example, are respiratory bacteria. Okay, so they tend to work really well with respiratory tract infections. Some of these Toxoplasma coccidia, these are actually protozoa, and they tend to cause, for example, in cattle, they tend to cause a little bit of problem when they are 3 months old or so, 5, 6, 7 months old. So what was really common at some point was to put sulfa, and because you can actually take it orally, to put sulfa in the water. You put a little bit in the water so you would prevent, coccidiosis, which is this disease caused by coccidia, which is actually also a zoonosis. It can pass from the animals to us, okay? And causes like very, very bad diarrhea and so on, weight loss and so on. So rapidly absorbed in most of the species. This is, sometimes we're going to go into, and we're going to talk about distribution, metabolism, and we talk about, it can be acetylation, it can be methylation, it can be also. It's not important for you to know exactly what type of biochemical reaction it goes on into how you metabolize that molecule. I think it's going to be all important if that thing is important enough to say, because of this antibiotic is like dangerous. So there's something that goes wrong there. So we don't need to know all this. In this case, that's fine. The most important thing is that you can take orally, you can combine with this. It's pretty good for respiratory urinary tract infection, even gastrointestinal. You can, and generally speaking, you have to metabolize, especially by the liver, and it's excreted by the kidneys. The binding, so it's not binding, it's binding to plasma proteins. One of the things that happens with molecules that tend to be strongly bound to plasma protein is that you normally have to take more of the antibiotics to reach a concentration inside of you that is enough to kill bacteria for a certain period of time. The other part, before I go to your question, is half-life. And this is where some of that will affect, depending on, how it is metabolized and excreted, it will affect your half-life. Because in practice, your half-life is what's going to determine how often you have to take the antibiotic. The way in which, people have done this is like this. They do tests and they try to see what is the minimum concentration that you have to keep in your body of that antibiotic to have a pretty good action against the bacteria. Okay, so in order for you to do that, you have to keep at a certain frequency that you have to take the drug. It tends to be the most problematic thing for you to do in terms of comply with the protocol of antibiotic administration, because if you keep, let's say this is the line of minimum concentration, and you keep doing this, normally the amount of time that you were below is enough time for the bacteria to regrow. And then you start having problems. The longer you take, you're going to be half cured, bacterial resistance, blah, blah, blah. Then you have a whole load of problems that arise from there. But it's because of metabolization. You had a question.
I was wondering when bacteriostatic antibiotics be preferred over bacteriostatic.
I think it depends on, in specific cases. Let's say you have an infection with, let's say, gram-negative bacteria. And remember when we talked about the bacteria themselves, what is one of the, and where is a portion of the antigenicity from gram-negative bacteria comes from what? Remember that, in gram-positive bacteria, you have some of the type of saccharide, polysaccharide. So in gram-negative bacteria, you have what?
It's LPS.
It's LPS. For gram-negative bacteria, is LPS. And LPS is what? It is a portion of it is like glycoproteins, lipoproteins that you have coming out of your outer membrane. If you kill the bacteria, what do you do with LPS? You massively release LPS. Because, that thing is in the membrane. obviously you're causing some antigenicity, but if you kill them all and all of a sudden you have that thing going everywhere, you actually cause more harm than actually stop the bacteria to grow. It is different. It's almost like you would like that bacteria to have like a control death, almost, than actually killing them all at once. So this is one of the cases where you would like to have your bacterial growth to stop, your immune system can take over a little quicker than actually killing them all. Because the way LPS actually causes all that inflammation is when bacteria actually dies, and then you have the LPS being released. So that's one. It's probably one of the best examples of why you would like to choose a certain bacteriostatic versus bactericidal. So this is one case. The rest, I would say, bactericidal and bacteriostatic. If that's not an issue, then it's much more about the other things: action, absorption, metabolization, half-life. That's going to be the case. Okay. Okay. So basically, that's what we have to say about sulfa and trimethoprim, and tends to work still today. Is used. It's a pretty good drug. It's a very old combination. Actually, this thing, it goes back to some of the stuff that we were talking before. Medicine has gone a long way, but we still have very old tools, today. This is another class of drugs, and probably this name like enrofloxacin or difloxacin. This floxacin kind of termination is one from a class of drugs that we call fluoroquinolones. So this fluoroquinolones is like widely used. They tend to be like also broad spectrum. They are more like on the bactericidal side because they mess with DNA, synthesis. So they end up not only affecting obviously the replication of those, but they actually kill, the bacteria. Distribution: central nervous system, bone, prostate. Also, they have rapid oral absorption. And in some ways, there is one thing that has to be said about the drugs that you can take orally. They also somewhat tend to go into the stream of, if it is rapidly absorbable, they also tend to be very penetrable into other tissues. For example, everything that treats the central nervous system. So some of this enrofloxacin is one, chloramphenicol, which we're going to see later, is another one. It is the ones that, they basically cross membranes like crazy. Okay? Because in order for you to cross the blood-brain barrier, it has to be, not everything crosses. Lots of the other, for example, molecules that we saw, that we'll see, and you will see, is one of those that, as very few actually crosses really well. And in this case, especially when you're trying to, for example, meningitis, and you have to have a certain kind of antibiotics going to the central nervous system, the way it is distributed in the body, is actually more important than how well it acts against that agent. Because it is even better to have a okay drug, but actually reaching the bacteria, than having the perfect, antibiotic, but not even reach the bacteria. Okay, that goes also for the case that we were explaining before about the urinary bladder. Some of the drugs, they simply do not go to the urinary bladder because they're metabolized first, and by the time they reach there, especially the lumen and where you might have like lots of infection, you may have a problem there. So that's why I said the dynamics in the very beginning of the class and the kinetics, they are more important than normally we give credit for in terms of which drug we use from an antibiotic point of view. Okay, so this is one of those examples too. So again, respiratory, urinary tract, usually when that happens, this is good, okay? Can be readily absorbable, and in this case, obviously, just the fact that it goes into the bone is it's probably a good measurement of how deep that thing can go, okay? All these things, yes, it can be orally. All the other drugs, I think with the distinction between the administrative routes, unless it is something completely specific, as I said, you know, when you go to some certain types of anesthetics, that goes either the spinal cord, like epidural anesthesia, or you go into you're going to inhale, which is very specific to a certain kind. The oral versus the others is normally where you have good leads to how that molecule works. Okay? Because if you can take orally, it means that the molecule is not stable, but it's non-ionic enough to be readily absorbed. So how it takes once or twice a day, the other part, if he says that you can take once a day, what does it tell you about the metabolization of the drug? Probably slower. There's something there that you probably, you know, when you call the ethylation or de-ethylation. This de-ethylation is not exactly the most common biochemical thing that happens in the liver, you know, in order to metabolize something. Have other things that it does more often. But this thing is not so much. So that is probably the reason why it can spend more time circulating. And by spending more time circulating, it's a big advantage that you don't have to take it as often. Now, we know this from a physiological standpoint, great. From a practical standpoint, the fact that you can give once a day is an enormous plus. Okay, so even for us, if you were to say like, oh, I have to only take once a day, it's much less likely that you forget, and it's much more convenient. In terms of an animal, is even more, because the animal then you have to remember, and not all of these drugs, they are either healing or they taste good or normally it's the opposite. So the stuff is like, this is a good stuff. This is the kind of good stuff for practical reasons. Okay, very practical reasons. Normally kidneys are the one more that, you know, the previous one was also the kidneys, the main route of excretion. This one is also the kidney. And then I always throw something there. Oh, difloxacin is 80% recovery in the feces. It's more into the bile. It goes more into the digestive system. The blood, liver. Then the liver actually throws that thing into the bile salts, and then it goes into the feces. But when would this, and I don't have much experience using difloxacin, but this is the kind of stuff that, you know, probably if you have something like an animal with kidney insufficiency, where you have problems with the filtration and excretion of things naturally, you would probably try to use drugs that depends less on the excretion through the kidneys and more through other routes, so you don't overload something that is already not working well. Okay, so you can take some of these little details into consideration again, into how or when these antibiotics. Now, when we're thinking about all of these things, what comes to your mind? You know, because this is something that we take a little bit for granted when we discuss antibiotics, because we take it since we were young, we always had it available and so on. But what does it tell you? And we're going to go through this also with the anti-inflammatory at some point. Well, what does this tell you about the class of drugs, antibiotics? That they are, for the most part, not entirely, but they are a little bit toxic to you. It's the kind of stuff that your body is trying to really get rid of relatively quickly. It's not the kind of stuff that you say, oh, your body really enjoys having difloxacin inside it. It works, is not tremendously toxic to you, but it's also not something that your body is like, oh, it's nice. It's like eating a donut. It's all good. No, it's the kind of stuff that requires your body a little bit of work, to take it. So, and that's the part that, I remember one of my professors said, we need to take this idea that antibiotics, anti-inflammatories, and all this stuff that we take it a lot with a little bit more caution, because they are not necessarily the kind of stuff that, oh, we take it and my headache goes away. I think it's okay the way we do it if you take it just every once in a while. But if you are the kind of person or the kind of animal that takes this all the time, the animal or you will pay a price eventually. Okay? This is not the kind of stuff that goes very easily on your body. Okay, so sulfa, trimethoprim, now fluoroquinolones, and the next one is probably the most famous class of antibiotics that we know of, which is the beta-lactam antibiotics. And to begin with, beta-lactam tends to be, the name comes from the beta-lactam ring inside of this molecule, which is it's just a 4-atom molecule, ring. And what it does is it's part of the molecule of this antibiotic. Okay? And that's why where the name comes from. The stuff this is the one that was first kind of discovered, penicillin, eventually is the staple, let's say, that's what is way of antibiotics. And penicillin is this, it was probably, to begin with, it was discovered almost by accident. It prevents bacteria cell wall synthesis, and in this case, compared to sulfa and compared to fluoroquinolones, is the first one that you say is not necessarily, or at least initially, was not broad spectrum. It tends to be more focused on one class of bacteria, and in this case, is much more active against it is against cell wall, gram-positive bacteria. Because it depends, the gram-positive depends much more on that cell wall to survive, or is a more structural part of that cell wall, of that bacteria. And then you have what we call natural penicillins, and you have some, that you can also call it next generation penicillins or even synthetic penicillins, okay, which we give the name cephalosporins. In general. In the cephalosporins, we have generations, which is first, second, and third. Fourth is basically, it's not exactly there yet, but first, second, and third it resembles more or less when they were first discovered and then produced. Sometimes they overlap a little, but that's the name that they give to some of these drugs. Natural penicillins, so you have, for example, penicillin G. Penicillin G is really probably today, in terms of relevance of these natural penicillins that are still used, the one that we continue to use every now and then, either for veterinary medicine or human medicine. And you have also benzathine penicillin. This is, I remember when I was younger, I used to take that one, which hurts like crazy, because it came almost into an oily solution. And you could take that one almost like it was once, and it would last for a week, because the vehicle of that thing was so thick, and it would just release slowly, but it was horrible, it was super painful. But it's one of those types of penicillins. These aminopenicillins is probably some of those that you guys and we are, especially in humans, in the veterinary medicine too, which is the aminopenicillin. So ampicillin, amoxicillin. So these are the ones that we take as like water, in human medicine. So this is very effective, but also today is starting to have a few problems with resistance. they tend to be, they were some of the first ones. As I said before, you have some of these natural penicillins. They tend to be, obviously, if they break the cell wall, they basically kill the bacteria, so they are bactericidal. So they're mostly with gram-negative. And then there's always these kinds of, these are the type of penicillins that we basically, we talked before. If you go into the medical field, really well-known types of, penicillins that are still used, so have lots of clinical importance today. And then you have some, for example, take for example, these anti-staphylococcal penicillins, or even some penicillins that act on gram-negative coccus and spirochetes. So this is the kind of stuff that starts like almost, it doesn't necessarily make a whole lot of sense from understanding the molecule and how they act, but because of the clinical use, they said, oh, it works well in this specific thing, or this one works well in this other specific thing. So you're going to have a lot of that into antibiotic use. So, but is this the most important thing for you to know? No. Because by knowing the rest, oh, I have an exception here. Okay, I got it. Different, probably have some sort of action to a specific bacteria, and that's it. Okay, but you're going to have lots of that, lots of these little twists and turns. Oh, don't use these antibiotics. Like I have a group of my friends from vet school, and they are always discussing what freaking type of antibiotic they have to use in their dogs. They have like lengthy discussions. Just use one. But eventually, there's always discussions. There's never like one option only. Okay? But as long as you understand the bigger picture of those things, you will be covered. So aminopenicillins, so for example, they tend to have a little bigger spectrum. Amoxicillin and ampicillin, super duper used, in vet medicine and human medicine. This, probably you have heard about this clavulanate acid or clavulonic acid, that amoxicillin plus clavulonic acid. You probably have seen, or you have taken these at some point. Very, extremely common in the type of antibiotics we take. Why? Is somewhat the same way that I put together, like for example, sulfa and trimethoprim, that they both act in different pathways of the same molecule, so they act synergistically. In this case, what happens is that this clavulanate acid, what happens to this molecule is that it is a beta-lactamase inhibitor. Okay, what is this? And this is one of the other twists that we have also in when we classify bacteria. Certain bacteria, they produce that beta-lactamase. And the beta-lactamase basically do what? It breaks beta-lactam antibiotic molecule. Okay? So it is what? It is their anti-antibiotic. Okay? It is the bacteria trying to defend themselves against that. And you have like thousands of molecules and enzymes that can act as beta-lactamase. And the more we create molecules that have this beta-lactamase, more resistance to these guys you will create. So you create several types. So in this case, the clavulonic acid, what it does is, it is an inhibitor of some types of beta-lactamase, which basically means it can act also synergistically by first blocking the enzymatic effect that bacteria may produce, and then on the other hand, amoxicillin or ampicillin can then do the job against the bacteria themselves. So penicillins, just the penicillins or aminopenicillins, They tend to not to be used so much on an oral route. Okay, you can reach plasma concentration by intramuscle, IV, or subcutaneous. So basically speaking, it is not good enough to cross the gut barrier. So it's not used all that much. You can also think, by not doing this, again, I'm trying to make it hooks, so it's easier for you to remember certain things. It is probably not going to treat you with a central nervous system kind of problem. Okay, so it has a little bit more problems because of the molecule themselves. Then you have some of those, which is like cephalosporins. They tend to be very expensive, antibiotics. Especially, particularly in vet medicine, they're not exactly cheap. So they used to be more gram-positives from the same first generation. They are somewhat, in terms of action, close to amoxicillin and ampicillin. And then as it goes, probably they developed with first generation, became then resistant somehow, and then they second generation, and then, which is a little bit, have even some gram-positive action, and then it goes to the third. The idea here is that they try as much as they can to produce new classes of antibiotics that can have more like broad spectrum, but at the same time is specific enough not to cause too much resistance. The problem is that it doesn't really matter if you use it a lot of a certain antibiotic. It's very likely that the bacteria will find a way to create some sort of resistance. It's a unicellular thing that acts or have a lot of interaction with the neighbor cells, and they are very dynamic. So they eventually find a way, to actually find some sort of resistance to it. Same way as the other, metabolized in the liver, kidney elimination. You have some types of beta-lactam antibiotics, not necessarily cephalosporins, that also treat some, urinary tract infections, but they are not necessarily the first option. Okay? They tend not to be the first option for it. Very good. So let's take a quick break. And the next one that we're going to see is tetracycline, which is also very famous, very, very popular antibiotic. Yeah.
what people have to say is all.
It's all over the place. Yeah, but it really isn't a clear cut. For the most part, I don't know if they have done meta-analysis on all this, but I think they wouldn't find that much support for it.
I was reading one where they said it was only to improve only on those clinical.
Yeah, but even in clinical metritis, like the reason why your prostaglandin, when you have clinical metritis, is super high. Your endogenous prostaglandin is very high. You just don't have that much action anymore. So that's a problem so you're giving prostaglandin.
So then in theory would like your prostaglandin is pretty high, like giving just to an extent or like part of it.
But for metritis?
Yeah, it's like the idea is like, well, at least from what I'm reading, is like to get them to open, like to come into heat, to open, and then they can start to let out whatever's in there, the infection.
Yeah, but think about it. How you're gonna let it open and let it all out? Treating metritis is one of those things that is super controversial. Like people have used what is the rate of self-cure for clinical metritis? It's like 60%. No, it's like 60%. But if you use antibiotics, 70%. Like there's a bunch of questions. Should you or should not use all that? It's kind of messy.
I can't believe it's already November 5th. The semester's almost over. Where did it go?
I know. Okay, so let's finish this. I'm tired. I'm hungry now too. Okay, that's good. Okay, so let's continue. Had a super quick break now, but let's continue on this. So tetracycline. So sulfa, metoprene used to be bacteriostatic, or could be fluoroquinolones, quinolones also. No, that would be like more bactericidal. Beta-lactam tends to be bactericidal. Now tetracycline again tends to be bacteriostatic. In general, when you go into protein synthesis, they tend to be more on the bactericidal, bacteriostatic side, but you're going to have one class that is actually bactericidal. So overall speaking, that's how it works. From protein synthesis tends to be, but you have some exceptions with it. So what they tend to do is they mask with the connection between the ribosomal RNA and the transporter RNA. So they don't allow the actual amino acids to bind together and to form a protein. So that's how they basically do this. We're not going to be talking too much about this aminoglycosides, but tetracycline tends to be one of the major ones for this class, this 30S inhibitors. You can give in most of the routes, but in general, it tends to be IV or intramuscle. Tetracycline, oxytetracycline is the other variation of tetracycline that is actually widely used as well. And now you're going to see that sulfa, penicillins, fluoroquinolones, like we talked about, some of the specifics, but we talked very little about certain risks, toxicities, and stuff. Now we're going to start to talk about certain classes that you always have a caveat here and there. For example, this is one, tetracycline is one that, for example, you cannot give it IV super quick. Okay? If you give it IV super quick, normally the animal not necessarily die, but it falls. Because you can actually bind a lot of calcium, IV, and all of a sudden you have a little bit of hypocalcemia, going on. So this is one of those little caveats that goes along with certain types of antibiotics, and that happens a lot in many ways. This is another class of proteins that also binds a lot. So you have certain types that look at the amount of protein binding in some types of these tetracyclines. It's a lot. Again, remember when I said if it is heavily bound to proteins, they tend to have less effect, so you have to give it probably a little more. Good stuff. It has a long half-life. You don't have to administer several times a day. You have the elimination lots by the urine, but quite a bit on the feces, so they tend to be a little bit nicer to the kidneys. This is what I was saying, like IV administration. You can cause hypotension and collapse because you sequester, calcium available. So I remember giving tetracycline, to cows IV, and sometimes what you do, you keep it, you give it really slowly. Sometimes you keep it stethoscope in the heart, because sometimes it messes with you can start having arrhythmia in your muscle heart. So it's the kind of stuff that, you can give it, but it comes with a little bit. Again, go back to that little talk that I gave there. They are not super nice. Antibiotics come with a certain price. They're not molecules that we should take it lightly. This is another one that it's a good class of antibiotics. It's used quite a bit. But you see, one of the things before we go, so they also, aminoglycosides, they also tend to mess with the 30S subunit. So, but in this case, they tend to be bactericidal in activity. Is an exception of this class of antibiotics. Most of the classes on the 30S, they tend to be bacteriostatic. And a few things that happen that is, for example, this is the kind of stuff that, yes, it would probably be okay to know. Why? Because of their absorption into the cell, because they tend to be quite specific to aerobic gram-negative bacteria. This one. And I'll tell you one of the reasons is that for this molecule to actually enter the cell, it needs a transporter that is dependent on oxygen. So if you have anaerobic bacteria that has no oxygen around, it basically don't let the molecule get into the cell. So in this case here, so you do require this oxygen requiring transport process, and in between the two, and basically this process here, this oxygen requiring transport process, in general, it occurs in between the plasma membrane and the outer membrane. So you have a space there that you need to have oxygen around, in order to happen. So it tends to be a very specific thing. The other part, but one of the gentamicin, neomycin, I remember using some of those. The only problem with that class of molecules, and I remember this really clearly, is the fact that they can be nephrotoxic or ototoxic. So they can be very, very damaging to the ear and also to the kidneys. I am not quite sure why it is so ototoxic. is very, damaging to the ear canal. But one of the things is there's a problem with aminoglycosides. And one of the problems is there is a lot of individual variation on how you metabolize and excrete that. And that's why probably you have quite a few problems with, kidneys, and sometimes it accumulates in different ways in certain bodies, and apparently the ear is one of these sites for whatever reason. And the stuff is physiological and pathological interference. People with different conditions, let's say you are obese, you are diabetic, you have like some sort of chronic condition, the absorption and the actual distribution of this drug through your body can vary by 1,000-fold, depending on the kind of condition you have. So it is sort of a weird molecule. It can work really well, but I remember having this kind of aminoglycosides as a second or third option of a certain antibiotic, depending on, it didn't work with the first, it didn't work with the second, and when you go like, okay, this is going to be a little nuclear bomb, so let's see what happens. But it's almost never the first option because of this kind of weird ways in which the molecule reacts. So it has very little to do with how it acts in the bacteria, but in how the dynamics and excretion occurs in the body. It's kind of very unstable molecule. Okay? And then you say, Ronaldo, but why do they still use? Well, because in some specific cases works well, but again, it's not like beta-lactams and penicillins that or penicillins or sulfa that is relatively quite safe. These ones here have a little bit more problems. So this is our approach. So it's a weird molecule. Obviously, they tend to have like quite a bit of, sort of, tend to be very ionic in nature, and that's why the distribution is kind of weird, and that's why it doesn't get very well absorbed orally. You have some, parenteral routes, so this is, you can have like even like intercavity or topic administration. Neomycin is one that you probably have seen in some of those topic creams that you use as antibiotics, and very, very commonly to have on topic use. Why? Because then the absorption is very limited. The action is on the exterior. So you have less of a problem of all that absorption, distribution, secretion. So it is one of those antibiotics that you can use quite a bit of topical, even over-the-counter kind of, creams. Oh, that is, guys. So this chloramphenicol, this one here is the very last class of antibiotics. I think one of the features for this class of antibiotics is, again, along with fluoroquinolones that, is very rapidly absorbed. It can reach even the central nervous system. This is another one that actually it used to be quite often to treat central nervous system diseases, especially obviously of bacterial origin. They tend to, inhibit protein synthesis. They have, and then, oh, very nice. So they are widely distributed, very or highly lipophilic, perfect to enter the central nervous system. So they're pretty good at that. However, and this is one thing that is from a usage standpoint, the fact that they have very rapid, and this glucuronidation is a very potent method that the liver does to metabolize stuff. So the liver is pretty good at metabolizing that chloramphenicol. But the most problematic thing is this chloramphenicol, they can actually affect the actual cells, the mated cells, because the the way in which they do certain things, especially in this 50S ribosomal subunit, you can get instances where you can cause some toxicity, in the animal by using a little bit too much. It is not the type of drug also that you see out there very common. You don't, unless it is, from what I remember in terms of usage of these antibiotics, was specifically to something that you have like an infection in the eye or in the central nervous system, like inside the eye or in the central nervous system, that it has to penetrate into very specific places and weird places of your body. Otherwise, you almost never would use that antibiotic because the risks for certain things are almost overcome the benefits of it. So the first 3 or 4 classes of drugs, we saw that, up until tetracycline, they work really well. They do things very last. And then tetracycline, you start, if you give it an IV, you have problems. And then you go aminoglycosides, chloramphenicol, and then you start having like weird stuff happening if you use some of those antibiotics. And it is the nature of these drugs. Okay, the anti-inflammatory, which we can maybe start, or we can maybe just give it a break. But we might do it. But the stuff is like the anti-inflammatories is the same way. Anti-inflammatories, then we're going to go into a different route of drugs. And the first slide, let's go to the first slide only, so we have at least a start from next class. The anti-inflammatory drugs, we basically divide those anti-inflammatory drugs into steroidal and non-steroidal anti-inflammatory drugs. So in general, we can short them by, sometimes it's very common in books for you to call the steroidal ones GC or glucocorticoids, and NSAIDs for the non-steroidal ones, okay? Again, the nice part about this is that widely used, most of you have very familiarity with, with the molecules of these drugs. But anti-inflammatory drugs, antibiotics, you need some degree of knowledge of the bacteria, but then the rest is like a little bit of pharmacodynamics, kinetics, and you can take almost like the study of antibiotics almost by itself, like it's a big package. Anti-inflammatory drugs will require you to know a little bit more of, for example, eicosanoid or prostanoid synthesis. When I say eicosanoids, prostaglandins, leukotrienes, thromboxans, which, they are weird names, but they are not complicated. But they are very central to how an inflammatory reaction occurs. Okay? Every cell in your body is able to do that. Why? Because it is part of the equipment that your body has to survive, basically. So if there's an injury, either a trauma or a bacterial infection, a viral infection, this eventually will be triggered. Okay? So in this case here, you have, and I think before we go into the types and other things, is cell membrane. The cell membrane phospholipids. A big source of stuff that happens inside of your body comes from the plasma membrane. Okay? Some activation of second messenger pathways comes from the plasma membrane. Protein kinase A, B, and C, they are activated through things sometimes that are anchored or activate stuff that are in the plasma membrane. If you think about this, and let's say this major phospholipase or this major, not a phospholipase, but a fatty acid, arachidonic acid. This arachidonic acid is basically it's a component of your cell membrane. you have all sorts of fats in your plasma membrane. One of them is one that we call arachidonic acid. You have stearic acid, you have linoleic acid, you have oleic acid. So remember those C16, 0, C18, 0, C18, 1, C18 through, linolenic acid, all that shit that people talk about you take. Oh, take this peel of fish oil because it has omega-3, omega-6, omega, oh. It's in that class of molecules. Why do you take and why do you have like so much stuff going on into that area? Is because when you take certain types of oils, you incorporate that into your plasma membrane. By incorporating the plasma into the plasma membrane, certain types of fats, you can modify a little bit this. So you see where the central knowledge before we go into knowing what an anti-inflammatory, an NSAID, blah, blah, having this stuff of the cell membrane is super important. So if you know this concept, everything else becomes easier to understand. So what you're only doing with NSAIDs and steroids is blocking certain enzymes. So as opposed to antibiotics that you're talking about DNA synthesis, protein synthesis, folic acid synthesis, and a cell wall, in this case, we're most of the time talking about blocking certain types of enzymes, such as cyclooxygenase. You probably have heard this as COX-1, COX-2 enzyme, or lipoxygenase to a much lesser extent, but it can happen too. And then you have the steroids. But in the case of steroids, yes, they do block some of these phospholipases, but they also block, actually, they are much more potent. So for example, if you do organ transplant and you need to put your immune system down, so you don't want to have rejection of that, you use a lot of glucocorticoids, like a lot. You basically kill your immune system. For why? Why? Because it can go to actually, it has receptors in the defense cells, it goes to the actual DNA, and it messes with the expression of pro-inflammatory, anti-inflammatory genes at the DNA level. Then you're going to have less of stuff. So your immune system, you block your immune system at a much deeper rate. So in general, for us, it's very uncommon for us to, oh, I have a headache, oh, let me take glucocorticoid. It's too much. You're messing with probably the wrong thing. Your inflammation, you're not only going to kill inflammation, you're going to kill your immune system with it. So that's the difference between the two big classes. So two big classes, idea of membranes is super important. Cyclooxygenase, maybe lipoxygenase. So this is the beginning of the next class. And from this, it's relatively quick. You're going to have like some specific information about, they have super great activities, something that we take and animals take every day, but they also have drawbacks, especially if you do like long-term usage and if you take it too much at once. So examples would be if you take like glucocorticoids for too long, you start having problems even with blood pressure, edema, and other things. If you take Tylenol too much, you maybe can eventually even damage your liver indefinitely, depending on how you do it. Okay, so same way as antibiotics, great stuff, dangerous, depending on how you do it. Okay, so we'll take it then for the next class on Thursday. We'll finalize this, and probably we're going to have time to do, at least one or two case studies there. Okay.